This lesson continues what we learned in Part 1 with different types of isomers and using the flowchart to help us identify those. The next group of isomers we're going to look at are all known as stereoisomers because they have to do with the orientation of groups relative to one another. Let's start with geometric isomers. For geometric isomers, there must be a double bond or a ring for the opportunity to have a geometric isomer. As we'll see in some examples in just a minute, the presence of a double bond or a ring does not guarantee that you have geometric isomers. So let's look at cases where we do have geometric isomers as a result of a double bond or a ring. In the molecules on top, we're going to look at the orientation of the CH3 groups relative to one another. In the molecule on the left, we see that the CH3 groups are on the same side of the double bond in our structure, and this is known as cis, which means same. When we look at the molecule on the right, we see that the CH3s are on opposite sides of the molecule and opposite sides of the double bond, and this is known as trans, which means on opposite sides. Unlike a single bond, the double bond prevents that free rotation that occurs when we have single bonds. The double bond locks us into a specific orientation, therefore molecules will be locked into either the cis or the trans orientation. The same thing occurs in a ring. When a ring forms, the bonds in the ring, although they're single bonds, are limited in their rotation. They cannot freely rotate as if they can in a chain compound. Just like in the previous examples, we can see cis, where the two non-hydrogen groups are on the same side of the ring. So we see a perspective drawing here. Both of the groups are on the bottom of the ring, pointing in the same direction. They could also be pointing in the up direction as long as they're both on the same side of the ring. We also see the trans option, where the two groups, the two non-hydrogen groups, are on opposite sides of the ring. So these are examples of cis and trans geometric isomers. Let's look at some examples where a double bond or ring does not guarantee a geometric isomer. In the pair of molecules on the left, we see one non-hydrogen group attached to the ring. Because we don't have anything to compare it to, another non-hydrogen group, we cannot describe it as either cis or trans, so it cannot be a geometric isomer. In order to have a geometric isomer with a ring, we need two non-hydrogen groups. They can be on adjacent carbon atoms or non-adjacent carbon atoms. In the example in the middle, we also see that we do not have a cis or trans isomer because we have two CH3 groups on the left. If we look at the molecule on the top, we could compare the two CH3 groups as being cis and trans. And so if we can describe it as both cis and trans, then it's neither. This will occur anytime there are two groups on one side of the double bond that are exactly the same. In our last example, we see that the rotation is actually happening around a single bond. And because the change is happening away from the double bond, it's not going to be a geometric isomer. In order to be a geometric isomer, the change needs to be involving the carbons in the double bond. Here, this is a result of the rotation of a carbon-carbon single bond. So these are not geometric isomers. The last group of isomers on our flowchart are called optical isomers, and this is because of the way they behave in light. The first thing we have to ask is, are the compounds non-superimposable mirror images? When we have a compound with a chiral carbon, it will have a non-superimposable mirror image. We can have multiple chiral carbons, and when they are all the mirror images, these are known as enantiomers. So enantiomers exist in pairs, and they are two molecules that are non-superimposable mirror images. Let's look at an example of enantiomers. These two molecules are mirror images of one another, and they are non-superimposable. No matter how we are able to arrange these molecules, we will see that all of the atoms will not line up. During class, you will have the opportunity to build models and see for yourself that the molecules are not superimposable on one another. Pairs of objects can also be enantiomers, and there are objects that are not enantiomers. Our hands are the most common example of enantiomers. They are mirror images of one another, but they cannot line up with one another, so they are considered to be chiral and exist as a pair of enantiomers. Other objects can have a mirror image that is superimposable. If I took the mirror image of a glass, what I would see is it looks exactly the same and the objects are superimposable, so that would not be an enantiomer. Likewise, with a nail, if I took the mirror image of a nail, it would look exactly the same and the two objects would be superimposable upon one another. Before we talk about diastereomers and epimers, we need to understand something about Fischer projections. So these are drawn as flat images, but they really are hiding some 3D structural information in them. If I look at my molecule for D-glucose, which is shown on the left, the dashes and wedges show us something about the three-dimensional shape of the molecule. There is a way to transform this into the molecule on the right. Although the molecule on the right looks like a Lewis structure that does not explicitly show geometry, Fischer projections do show geometry, even though it's not easily seen in the way that it's drawn. You will not have to convert from the version on the left to the version on the right. But what you should realize is that the way this molecule is drawn, this is a carbohydrate molecule, the way this molecule is drawn does represent something about the 3D structure. So when we look at isomers of these molecules, we will understand more about why the things are on the left and the right. Let's look at the enantiomers of glucose. On the left, we have the version of glucose we saw in the previous slide, where we have our groups all the way down. We have some groups on the left and some groups on the right of our structure. And when we want to have the mirror image, or the enantiomer of that compound, we can simply switch the orientation of the H and OH groups on each carbon. We'll find that the carbon at the very top, when we look more at carbohydrate structures, does not have 4 groups, so it is not chiral. And the carbon at the very bottom has 2 hydrogens, so it's also not chiral. It's only the 4 carbons in the middle that are considered chiral, and those are the ones where we'll flip the side that the H and the OH are on. So when we look at the top chiral carbon, we see that the OH was on the right in the first molecule, and the OH is on the left in the second molecule. And this is a mirror image of it. So even though Fischer projections do not explicitly show 3D structure, there is information about the 3D structure hidden in the way that it's drawn. We look at the next chiral carbon. We flip the H and the OH to opposite sides. The same for the third chiral carbon as well as the fourth. So these two molecules are mirror images of one another, and because of their 3D structure, they are non-superimposable, and so they are considered a pair of enantiomers. Diastereomers and epimers are similar to enantiomers. The difference is in the number of groups that are flipped. In an enantiomer, all of the groups flip from left to right because we are doing the exact mirror image of the molecule. When we look at a diastereomer, what we see is that some, but not all, of the groups are flipped. So we can have more than one, but less than all of the groups flipped and have a diastereomer. Epimers occur when only one of the groups is flipped. Remember, these are all Fischer projections, and although we don't see it, these do represent a 3D geometry of a molecule, unlike a Lewis structure which does not explicitly show 3D geometry.